Today, I'm going to share with you some of my research, which has relation with nanofluids, which are a new type of heat transfer fluid, which can be used for solar thermal technologies in general. But before I start, I would like really to thank Professor Ahmed Nawi, our role model in Morocco, for us as Moroccan researchers. I had a chance to meet with him when I was in South Africa, and I presented in some of his events that he organized. Thank you very much, Professor Ahmed Nawi, for all of what you are doing for Morocco. Thank you very much. So, as I mentioned, my talk will be dealing with nanofluids as heat transfer fluid for solar energy. I currently joined the YOM 6P as an assistant professor after spending more than 18 years in South Africa, and I'm very proud to join YOM 6P, one of the best institutions in Morocco. So, as you can see from this slide, YOM 6P, even if it is a new institution, they are doing very well when it comes particularly to human capital developments. Numbers are speaking here. The number of students around the years 2023, 2024 is almost 5,684, and it's even rising more. And if I'm looking at science and technology, we have more than 1,000 students by now. So which means as researchers, we have really to contribute to human capital development for Morocco so we can rise the technology and we can also compete with the developing countries in the future. Why not? So of course, I'm at YOM 6P working at ICER, the Applied Chemistry and Engineering Research Center of Excellence. Actually, it's a very, very good center. The infrastructure here it's really I was shocked when I joined here, the ICER. The infrastructure is just fantastic for any researcher who would like really to discover when it comes to R&D in general. And it's led by Professor Youssef Ben Mabkhout, of course. He's a good leader, and really, I found myself within this center in general. And there is a huge team now, a lot of students, postdocs, and what I found that most of them, if I can say all of them, are really talented Moroccan people who are trying to contribute to R&D in general in different fields, ranging from organic optoelectronics, advanced material and processes, smart material development, and process engineering. By the way, this center is trying to make a link between chemical engineering, chemistry, and engineering in general. So as scientists dealing with fundamentals, we interact with engineers, highly talented engineers, Moroccan engineers, who are helping us to develop newer technologies from the materials that we are trying to develop here within the center at YOM 6P. So of course, my role within the center is to contribute to the section of electrochemical, or the division of electrochemical energy storage and conversion, led by Professor Sadoun. Thank you very much, Professor Sadoun, for implementing such a beautiful division here within ICER. And of course, my contributions will be to use nanotechnology for solar thermal energy conversion and storage development, of course, since Morocco now is investing hugely in solar thermal, as you know, in general. So we, as Moroccan researchers, we have to be able to develop newer materials so we can contribute to high efficiency of these type of systems within Morocco. So if I'm speaking about solar thermal and how nanofluid will contribute in general. So of course, in Morocco now, the target is to use solar thermal, particularly to produce electric power. But one should really think about industrial processes where we spend huge electricity to produce thermal energy for our processes in industry in general. So one should think about small-scale solar thermal systems. The problem of these solar systems, they should be highly efficient. And here where nanofluid will contribute, as I will explain during this presentation. So if I'm speaking about industrial heat process or renewable industrial heat process, so of course, there are different industries in Morocco: chemical industries, food and beverage, machinery, mining, textile, wood. For example, if I'm speaking about chemicals, boiling or distilling, we need only temperatures around 150, which is lower, or medium, 150 to 400 for distillation. If I'm speaking about food and beverage, we spend huge amount of electricity for drying, boiling, pasteurization of milk and dairy food, and so on. Machinery is the same thing. Cleaning, drying, we need really heat for our processes in that case. When it comes to the mining sector, of course, Morocco is a leader in phosphate here. We have a fantastic, really organization which produce phosphate in general. And processes when dealing with phosphate, of course, thermal energy is very important, particularly for drying processes. And the drying can be done, it's either around this type of temperature, which is lower than 200 degrees, of course. Otherwise, we can also think about bigger systems which they can use even temperatures between 150 and 400. And of course, Morocco is rich in copper. For example, copper electrolytic refining, of course, it needs heat. And this can be done, of course, with solar energy, particularly solar thermal. Textile industry in Morocco is flourishing. And of course, we spend huge electricity there to really tackle this issue of processing textiles and matters related to that. And wood industry again. So what are the type of systems used for industrial heat process, or what are the systems which can have a potential to contribute to industrial heat process? We can use very simple systems such as flat plates system or evacuated tubes for very low temperature below 200 degrees. Otherwise, if we are trying to use medium temperatures like between 150 and 400, we can think about parabolic systems or Fresnel systems. So, by the way, in Morocco, here at UM6P, I was really happy to find that the Green Energy Park is actually, it belongs to UM6P. I have visited there and I found that they have really some systems which they can be used to test this nanofluid I'm gonna speak about, to see if they can really contribute to higher efficiencies of the system, so we can deal with this industrial heat process in general within Morocco. So we can create a new industry in Morocco for the heat process. And again, maybe we can come up with new products as heat transfer flows for these systems at the end of the day. So of course, while I'm here at UM6P at ICER, I would like really to focus on this part because the mining sector, OCP, are dealing with drying, and we wish in the future that we can implement systems where we can use this solar thermal energy for the drying process in general. So of course, as I mentioned, there are systems like flat plate, solar heating collectors, which they can be used for lower temperatures below 200. Of course, nanofluids can be used in that case. Of course, if we are trying to target temperatures above 200, maybe to, let's say, 350, we can think about parabolic systems where nanofluids can be injected at heat transfer fluid. So the mirror will reflect the solar energy. This solar energy will be converted by a receiver tube, which is coated with selective solar absorbers. So these selective solar absorbers will absorb the light energy and convert it to heat, which can be transferred with nanofluids, which are at the inner tube, receiver tube here. Otherwise, we can use also evacuated tube for lower temperatures applications in industrial heat process. And the mechanism is also here depicted here. Nanofluid or heat transfer fluid can be injected here, and it can be used for our processes in the once are implemented. So the question now, what are nanofluids? So nanofluids, simply said, is to take some conventional heat transfer fluids, such as oils or silicon-based oils, or ethylene glycol at a heat transfer fluid, or even water for lower temperatures. You take these heat transfer fluids as liquids and you add nanoparticles to them. For the simple reason, because solid materials, they have higher thermophysical properties compared to liquids due to their density. So if we add single particle, for example, like metallic nanoparticles or metal oxides, they will really contribute to enhanced heat transfer in general. Otherwise, one can think about hybrid nanofluids, which means that you can use hybrid nanoparticles. You combine different type of materials in order to have this type of hybrid nanofluids, which have even higher heat transfer properties for the nanofluids at the end of the day. So of course, there are plenty of applications of nanofluids, as I mentioned, in energy sector, like solar collectors, even fuel cells, and Morocco now is trying to deal with hydrogen technology. So nanofluids they can also be used as a coolant for fuel cells. As you know, fuel cells, they generate a huge amount of heat, and one really should think about how to cool them down by using heat transfer fluid with higher performance, such as nanofluids. One can really develop robust fuel cells for different applications when it comes to energy in general. Geothermal facilities, unfortunately, we don't have these in Morocco, but there are countries like Iceland, they use geothermal facilities. They have huge facilities there to produce electric power from the geothermal energy in general. As you know, the photovoltaic technology, of course, it suffers from heat. Solar panel, once the temperature is high, the efficiency is down sometimes. So there are researchers around the world thinking about using systems where they can implement systems to cool them down. But again, the cost. Cooling them down, it can help in increasing the efficiency of the PV panel in general. But again, the cost. So our engineers should really think of having systems to cool the PV without increasing the cost. So we can really implement these systems with higher efficiency in the future. And there are, of course, different applications of nanofluids, so I cannot cover them in this presentation due to the limitation of time. So as I mentioned, one should think, why nanomaterials? As I mentioned, nanoparticles are solid, of course, solid materials with a size which is very narrow. If I'm taking a molecule, for example, it has a size below 1 nanometer. Even we go down to like water molecule is around 0.1 nanometers. So if I'm looking at a virus here, which has a size above 100 nanometers, so the nanoscale or the nanoparticles, it's lie between this range here. So we develop materials which are between 1 and 100 nanometer for the simple reason. Having smaller size, you have high surface to volume ratio, which means the material it will have different physical chemical properties at that range. A bulk material will have different properties. If I take gold, for example, if I take a piece of gold at the bulk or at the macroscopic level, of course, if I do characterizations, optical, mechanical, electrical, of course, it will be different from a nanoparticle of gold. This is just an example. So targeting nanomaterials is to find newer thermophysical properties or physico-chemical properties, mechanical, electrical, magnetic, optical, thermal, chemical. Of course, in our case, we're trying to reduce the size of some kind of materials, metals, metal oxides, in order to enhance the thermophysical properties of these materials to be injected in conventional heat transfer fluid and to create nanofluids. So we are looking at increasing the heat capacity or thermal expansion, reducing thermal expansion, or increasing the thermal conductivity of our nanofluid systems by having higher thermal conductivity, which means this nanofluid can contribute to higher efficiency when it comes to CSP systems or solar thermal systems in general. So speaking about materials, of course, we have choices. So either you use metallic nanoparticles injected in conventional heat transfer fluid or base fluid like water, oil, or mineral oils in general. One can think about carbon-based materials such as single-walled carbon nanotube, multi-walled, or graphite. Unfortunately, of course, if I'm looking at the literature, these materials, they contribute hugely due to their what we call 2D dimension structure. So they create like a network within the fluid and they contribute hugely to enhancing thermal properties. Unfortunately, these materials are expensive to produce. So that is the issue. So I wish in the future that we can be able to create this type of carbon-based materials or allotropes of carbon in a cost-effective way, so we can be able to create nanofluid with even higher heat transfer properties or thermal properties. One can think about oxides and so on. So this is just a small table here showing you that like metallic particles, of course, they have higher thermal conductivity if injected to some base fluid like ethylene glycol at a volume fraction of, let's say, 0.3, an enhancement of 40% we can achieve with that. With aluminium, again, we can achieve even further, 45. But again, the volume fraction is higher than copper here, which means copper is better than aluminium in this case. So for oxides, of course, oxides, they have lower thermal conductivity compared to metals. So that's why we can see the thermal enhancement here, it's quite lower than metallic nanoparticles in this case here. So, but anyway, one should test different materials. Again, if I'm looking at oxides like aluminum oxides, it's cheaper to make by having 18% enhancement at 5% volume fraction. It looks good for me because the cost of making aluminum oxide is quite lower than other kind of materials. But anyway, we are trying at ICER here to implement some plans in order to test different materials from the periodic table so we can find out how we can do that. So of course, So of course, one should sometimes use computational calculations. Dealing with materials, different materials sometimes is time consuming and energy consuming. So sometimes we use computational analysis and we try to find out different or to study different type of materials through molecular dynamic to see if these materials can really contribute and how much they can contribute in terms of enhanced thermal conductivity. So we use molecular dynamic through what we call green Kibo model, which is depicted in this equation. It just shows you here that we can create a system like this that you can look at it here. So with the volume and the number of particles, so we study what we call heat flux. We study the heat flux, and from the heat flux we can do some integration, so we can get the thermal conductivity in general from this system here. So as you can see with me from this produced video from the calculations, so what we can observe here that how these nanoparticles contribute, just the principle. So the molecules within the liquid here is just water here. It's just a simple liquid, water. So the molecules of water, the vibration of the molecules, because heat is vibration in physics, is very well known. So the vibration is quite low if it is compared to the molecules absorbed at the surface of a particle here. So the vibration are higher. So this, it shows clearly that solid nanoparticles, they absorb more heat, they create more vibrations, and these vibrations are also transferred to the molecules of the liquid or the base liquid. So which means the nanoparticles are important in this case. So they allow the nanofluid to absorb more energy in order to increase the heat transfer in general. So, and this is what was making us to be interested in dealing with nanofluids in general and creating nanofluids. So of course, we studied different materials and we found very beautiful results. For anyone interested, we have a number of publications in this, and please feel free to check or to contact me so we can really discuss more about this. So making nanofluids in general, there are different ways. It's either you use laser-based methods or hydrothermal methods. So a laser-based method, of course, you have a source of laser, you have a target, you can do ablation in liquids, which means you can introduce nanoparticles directly inside the base fluid or the heat transfer fluid. Otherwise, you use a hydrothermal method. So we compared between these two methods. We found that a laser ablation, it's much better because it allows us to produce nanoparticles below even 10 nanometers. Below 10 nanometers, the nanoparticles are charged and they will have the property of electrostatic stability, which means we don't need really to add surfactants, and other materials to stabilize the nanofluid. When dealing with hydrothermal methods, sometimes it's difficult to control the size. We have high size distribution, bigger particles, smaller particles. It creates a lot of issues in terms of agglomeration and so on. So of course, we took the choice of using pulsed laser ablation in liquid because it has different advantages. You can use it to ablate metallic targets. You can use it to make fragmentation if you have bigger particles to make them smaller. You can do that with a laser ablation. You can, of course, create defects. As you know, creating defects, you create newer physico-thermal or physico-chemical properties within the material. And this can allow you to discover even newer materials with defects and so on. So pulsed laser ablation, you can select material from the periodic table, which means it is a versatile method compared to a hydrothermal method. So this is what it makes us to take it as a choice of making these type of materials. Of course, when it comes to the cost or why we use, again, this pulsed laser ablation, comparing between the pulsed laser ablation and chemical reduction or hydrothermal, as you can see with me, this green line here and the orange line, it shows you this is the nanoparticle mass for this is the nanoparticle mass, and this is the absolute cost of production. So as you can see with me for the chemical reduction, more you go for the higher production mass in terms of nanoparticles. So the cost, it goes higher. For the pulsed laser ablation, of course, the cost, it goes higher, but there is an event where the pulsed laser ablation, it's become cheaper than what we call the chemical reduction or hydrothermal technique. For the simple reason, particularly when you are dealing with higher scale production, for the simple reason, chemical methods in industrial processing or industrial processing of making nanoparticles, there are many processes involved, like cleaning, like centrifugation, and so on. So all of these things, they add to the cost of chemical reduction. For pulsed laser ablation, we don't need that because you are producing clean nanoparticles to the liquids, which means you are producing nanoparticles directly in one step. And this can really reduce the cost if you are thinking about involving this in industrial production of nanofluids for solar thermal or even other what we call applications of heat transfer in general. So of course, nowadays, laser systems, of course, are expensive. But nowadays, there are companies around the world who are producing these systems in a lower cost. So in this figure, it shows you the power of lasers produced worldwide and the relative price of them. So now we have systems with high power with the reduced cost, which means one should really think about this in order to produce nanofluids at a lower cost. So for us, we tested this method, of course, with other colleagues, collaborators from Germany. So the system is very simple here. You have a source of laser, so you can use a galvanometric mirrors here to scan the beam of laser on a target which is inside the flow chamber here. So this is the conventional heat transfer fluid. You can pump it through the flow chamber and you can do ablation of your target, so you can generate nanoparticles directly. And this, it can be continuous. You can do it for very long time, so you can produce highly concentrated nanofluids in general. And you can dilute them in the future to make high scale, of course. And we have produced different types of nanofluids like copper here, and there are some other nanofluids and silicon oil here. And of course, the scale, it's good enough. So the method was tested and it was working perfectly. Of course, we need to optimize more so we can produce different materials and so on. So of course, making these nanoparticles, one should really analyze them, characterize. We cannot say we are making nanoparticles inside a liquid without knowing what is there. So here, copper nanoparticles produced in ethylene glycol using these lasers, doing energy dispersive X-ray, it shows that copper there is pure, of course. Of course, if you produce copper and water, of course, you will have an oxide. Here, it is an ethylene glycol. We didn't really find any oxide of copper there. Of course, we have done some optical analysis. Copper, it has a surface plasma resonance which means it absorbs light around the visible region and shows clearly compared to the literature that these are nanoparticles of copper. So particle size distribution-wise, the particles are really below 10 nanometers using different wavelengths of lasers. Of course, the green light of laser gives us even narrow particle size, which is really beautiful there. Of course, producing this nanofluid. Sorry, colleagues, I'm speaking fast because of the time, but I'm gonna make sure that we finish this in time. So making nanofluids and claiming that these nanofluids are good for heat transfer, one should be able to analyze them. One should be able to analyze the thermal conductivity. One should really be able to compare between conventional heat transfer fluid and conventional heat transfer fluid with nanoparticles, which are nanofluids. So here we design systems to analyze that. So this is a guarded hot plate, which we designed at home. So it's a very simple system. So I'm not going to go to the details here, but this guarded hot plate, it means that you have two plates, a cylindrical plate where you inject some power to heat this cylinder, and you have a cold plate. If you inject your nanofluid between these two plates and you send some thermal energy through the power applied to the inner cylinder, the heat will be transferred from the hot cylinder to the cold cylinder. And there is a one-dimensional heat conduction equation, Fourier equation, of course. It shows you that if you have applied a power, which is Q here, by using this power supply, and this equation is so that the power equal to the thermal conductivity times the area of the cylinder, the inner cylinder, divided by the D. The D is the distance between these two cylinders, the inner and the outer cylinder, and you can measure the hot plate temperature and the cold plate temperature, as you can see here, so you can extract the thermal conductivity. Very simple. So we build it at home, as I mentioned, and we produced nanofluids, they were analyzed, and really we found some beautiful results for different nanofluids with copper, with aluminum oxide, with even some complex systems. And we published a number of papers on this research. And really we are trying even to enhance the measurement by implementing and by getting even better instruments. So we can be able to analyze precisely even in the future. Of course, using this type of systems, you have a margin of error. But we try our best really to find out that margin and to make sure that the measurements are almost precisely as much as possible at the end of the day. So as I mentioned, we have done this research with our colleagues in Germany, and of course, we used their systems there. I think last year, I have been there. We have done some research, just taking copper and of course, we have done ablation of copper in ethylene glycol, even in silicone oils. We use it our systems, as you can see with me here. This is the temperature, because you have to measure the thermal conductivity at different temperatures. Because if I'm using these nanofluids, as I mentioned, in CSP systems, for example, CSP systems, they work at different temperatures. They don't work at room temperature. One should find out the impact of temperature on the system, on the nanofluid. Sometimes these nanoparticles, that they can interact at different temperatures, and the nanofluid can lose stability in general. So here we vary the temperature and we measure the thermal conductivity with the system I showed you previously. So here what we can see here, these are copper nanoparticles in ethylene glycol, and at higher temperatures, even the thermal conductivity is getting higher. We achieved 30% and the stability was fine. We repeated this analysis from time to time, and the stability of the nanofluids, it was really good. So what I'm showing you here is just the diameter difference between different nanoparticle sizes here. The blue one, it shows that if the nanoparticles are bigger, the achieved enhancement is around 18%, which means smaller nanoparticles, they give higher thermal conductivity enhancement. And this is one of the reasons we selected pulsed laser ablation in liquid, because it allows us to produce nanoparticles below 10 nanometers. Here I am dealing with nanoparticles around 2.5 nanometer that we managed to produce using our laser system. So of course, the thermal conductivity, as I show you, it is enhanced hugely. The volume fraction, of course, it has also an impact. Here, it is really very beautiful at a very low volume fraction, 0.002%, while the nanoparticles at 2.5 nanometer, they give us higher enhancement, which is something fantastic. Is around, again, 30%, which is good. So these results are promising, and we are really trying our best really to test them within the Green Energy Park via the ICERIUM 6P. And I wish this project can go further here in Morocco, and we can achieve better results so we can produce, or maybe we can create an industry here in Morocco where we can produce advanced heat transfer fluid like these nanofluids, which can be commercialized not only in Morocco, but internationally. Of course, I'm here working with my colleague here, Dean Ibrahim, trying to produce some nanofluids using different type of lasers. So which means the research is still going on. Now we are implementing a laser laboratory at ICOSES 6P ICER. I think by the end of this year or earlier next year, we will be able to start producing this nanofluid here at ICOSES 6P using laser systems. Now we are using facilities in Germany at Duisburg Eastern University. Thank you very much to Professor Stephen Bachowski, who allowed us to use his systems. But now we have the know-how, so we are confident that we can implement this technology here in Morocco. So we have a dream to create an industry in Morocco where we can produce nanofluids, heat transfer fluids, advanced heat transfer fluid for our solar thermal systems here in Morocco and even worldwide. So of course, when I'm speaking about heat transfer fluid market, of course, one should think about the market. So from some studies, it shows clearly that the market will be rising quickly from here. As you can see with me, the market size is expected to grow from $3.2 billion in 2019 to 8.34 billion by 2030. So one should really think about it. So the compound annual growth rate of it is around 9.2%, which means it's going to be rising even more in the future. So one should really think about it, because nanofluids now, researchers around the world are really doing their best to bring them down to the industrial level and commercialization. So Morocco should be one of those countries. We should compete with developing countries, so we can also put ourselves on the map of developing newer technologies from Africa. And thank you very much.